Okay, so good morning, everyone. Thanks for showing up, and thanks to the organizer for inviting me. So my talk is definitely going to be about as high a temperature as you're usually interested in. Everything is close to the critical temperature for Bose-Einstein condensation in an interacting gas. And I'm going to talk about two geometries. So for most of the talk, I will talk about our experiments with potassium-39, where we have tunable interactions due to a very nice Feshbach resonance at about 400 Gauss. And these experiments take place in a conventional harmonic trap. I'll talk both about equilibrium and non-equilibrium effects of interactions on condensation. And then at the very end of the talk, I will also introduce a little bit our new experiment, where we have, for now, just rubidium-87, so no Feshbach resonance for now, condensed in a uniform potential. And I'll talk only about the equilibrium of this condensation. Now, after I sent this abstract, of course, I realized how long the talk was, and I overloaded it slightly. So one of these sections, which is a bit older, which is the equilibrium effects of interactions on condensation in a harmonic trap, I'm not really going to sort of explain in a detail that I would normally. The whole talk was dedicated to that, but I'm just going to summarize some key results that they need for the non-equilibrium part, which is more new. Okay, so just to get things going, let's start with a very basic picture of Bose-Einstein condensation in an ideal gas. This is going back to Einstein. So in an ideal gas, we have a purely quantum statistical phase transition, which in principle, at least mathematically, does not rely on interactions, but is just driven by the saturation of all the excited states in a gas. So here in this diagram, what I'm plotting is the number of thermal atoms n prime, the number of condensed atoms n naught, as a function of total particle number n at some fixed temperature. And so if the total particle number is below some critical value, we have just a thermal component. And then when we hit this critical value, Nc, then the thermal component saturates at Nc, and everything else goes into the condensate. Now, this is the maths, but of course, in reality, even if you wanted to, you cannot do equilibrium experiments without any interactions. So we have interactions in the system, and additionally, we are traditionally in a harmonic trap, and this has two effects on this diagram. The first one is that the critical point is shifted by the interactions, and the second point is that the thermal component is not actually saturated if you have a combined effect of harmonic trap and interactions. So we have spent actually at least a year addressing these 2 points quantitatively, but as I said, today I'm not going to explain so much as list the results that I will need as an input in order to understand the non-equilibrium experiments later on. So the first point is the shift of the critical temperature, which we have now managed to measure to pretty high accuracy, and basically to leading beyond mean field order. The mean field part of this shift, which is overall negative, the mean field is strictly negative, is theoretically exact. It's an analytical result, which was shown by Stringari, a company a long time ago, and has been seen before experimentally. To some extent, first by Eric Cornell, very early on, and then to high accuracy by Alain Espé about 8 or 9 years ago. And so more recently, we have managed to also see the beyond mean field shift, to the first beyond mean field order, which actually starts shifting the critical temperature the other way. And this one can also be actually related to theory, but that's quite a bit of work and actually a whole other paper. So I'm not going to talk about that, but the important message here is that we know how TC tunes with interactions to very high accuracy. And then the second point is that even once you reach TC and keep increasing the particle number, in reality, with interactions and harmonic trapping, the thermal component is not saturated. This is what we see here for some moderate interaction strength of 135 A naught. It's also some moderate harmonic trap with typical experimental parameters. We see that when we hit in Nc, rather than all the atoms going into the condensate, it's actually about half-half. This effect is also understood. We have also shown that the effect goes away if you extrapolate to the limit of no interaction, so it's not violating Einstein in any way. But again, the main thing for now is that we know exactly how strong this effect is. And so combining those two effects, we can construct something which could be called the equation of state. It's a equation of state. There's many things we call the equation of state, which is shown here, and which is basically telling us in equilibrium for a fixed total particle number, given temperature, and a given interaction strength, what should be the equilibrium size of the condensate, right? What should be the equilibrium number of atoms in the condensate. This is conceptually a very trivial equation. It just says that the total particle number is equal to the thermal particle number plus the condensed particle number. Okay, so that's obvious. But then the hard part, which involves all this work, was to figure out what is actually n prime for a given temperature and a given n naught and a given scattering length. Right? And it has two components. It has the critical value, which depends on interactions in subtle ways, and then it has this additional non-saturation component, which depends additionally also on how big the condensate is. Anyway, now we have this equation which worked quite well, and is going to be the input for our non-equilibrium studies. And this is just the graphical representation of this equation. It's a fixed temperature, n naught is a function of n for different scattering lengths, right? So the fact that these curves, the onset of these curves is shifted to the right, the decrease in scattering length is the TC shift, and the fact that these lines are not parallel to each other is the non-saturation effect. So with that understood, we can go into non-equilibrium studies, and there's two kinds you can do, and I will maybe talk about the less familiar one. I will definitely talk only about one, but I think it's the less familiar one. So one type of non-equilibrium experiments in my crude classification is a so-called transient non-equilibrium experiment, where you suddenly quench something, and that the speed of that quench, the sudden change in the system, say the total energy of the system or the Hamiltonian, is what induces non-equilibrium behavior. And then the system settles eventually to a new equilibrium. This is like what happens in an electric circuit if you flip a switch and the capacitor has to charge or discharge, right? And then you can study the non-equilibrium behavior between two equilibrium limits by looking quickly, right? And of course, the nice thing about cold atoms is that the quickly is not necessarily so quickly, right? We often have tens or hundreds of milliseconds or even seconds sometimes to study this, right? And so many groups have done this, including us. We have in particular used the quench of the scattering length, like so, in order to study some effects of bosonic stimulation in the formation of the condensate, in the so-called two-step picture of condensation, which older people will remember as a topic of big debate maybe 15 years ago. But what I actually want to focus on today, to explain one thing better in the limited time, is what I call the intrinsic non-equilibrium case, where the non-equilibrium effects do not arise because you have changed something quickly and the system just didn't have time to adjust, but where actually the evolution itself drives the system away from equilibrium. Right? And this can happen, for example, if dissipation is faster than equilibration. Right? Then just waiting doesn't help. Right? I mean, the system is not converging onto a new equilibrium. Right? That's why that's how word comes up. Right? That's why I call it intrinsically non-equilibrium behavior. And as an example of that, we're going to study a quantum analog of this picture. So this picture, according to the people on the internet, is showing superheated water which somebody has made at home in a microwave oven. Right? So this is just a mug of distilled water that somebody put into the microwave and heated it to above 100 Celsius. And then if you take it out, it looks just like water. You can't actually see any difference. But the reason it looks funny like this is that then they like sprinkle some salt or pepper into it, and they perturb this metastable superheated state, and then it suddenly evaporates. Okay. So now we want to study something analogous for a Bose-Einstein gas in order to understand it as a sort of generic simple non-equilibrium problem, but actually might also have some practical applications eventually. Because basically being superheated means that you have a condensate or you have a coherence under conditions when you normally would not expect to. Right? So you can, for example, extend the condensate lifetime by creating a superheated state, as I will show you later. So if you want to do some, say, interferometry, it's not bad that your condensate lives longer than it would normally. So let's stress a little bit more this analogy, but also differences with the superheated water, which is a bit more familiar to you maybe. So for superheated water, the definition of superheating is obvious. It's something that is still liquid above 100 Celsius. And so here we can draw that analogy for a Bose gas in equilibrium. The gas is supposed to have a condensed component only below some TC critical temperature, which depends on the particle number, or equivalently if the chemical potential is above some critical value mu c, which is pretty close to zero in a weakly interacting gas, but just for generic representation, I call it mu c here. And so in analogy with that, we're going to call something superheated if it has a condensate, even though the temperature is above Tc, or equivalently at a fixed temperature if the particle number is below Nc. that is the analogy, and it's about as far as it goes in some sense, because there is also an important difference, which is obvious to condensed matter theorists, and which in some ways actually makes this phenomenon more interesting than what you can study in conventional condensed matter systems. And the difference is that the boiling of water is a sort of this continuous first-order phase transition. And so if you have a first-order phase transition, then for the transition to take place, you need some nucleation centers. Otherwise, there's problems with surface energy, right? And there's some energy barriers, right? And so the way you stall boiling of water in a clean sample is just by removing these nucleation centers, right? So the water stays metastable in a liquid state because of energetic arguments, right? There's some energy barrier to the lower free energy state. Now here we're dealing with a continuous second-order phase transition, so there is no such barrier. Okay? So everything we're going to see has to be somehow purely dynamical non-equilibrium effect. Right? And sometimes when you tell condensed matter theorists you've seen superheated Bose-condensed gas, they ask you, but isn't Bose-Einstein condensation a second-order phase transition? And that should end the story, right? But it turns out it doesn't, right? If you look at the dynamical non-equilibrium effects. So before showing you any data, I'm going to introduce sort of the basic theoretical picture in which we're going to think about these effects and eventually actually manage to reproduce them quantitatively. And I should say, to prevent some questions from experts like the second speaker today, I'm presenting this with the benefit of hindsight. Okay, so I'm not arguing here from first principles that this minimal model has to be sufficient, okay, or that we knew that it would be sufficient, right? It was more the case of us doing the experiment, seeing something funny, then asking ourselves, can we do some simple theory ourselves? What is the minimal model that captures this, right? And it turns out that the minimal model, which will be more familiar maybe to experts and maybe dubious to non-experts, and maybe dubious to experts, it turns out to be enough. So the success of this picture is a result rather than the assumption of our work. So what we have here is we have simply divided the system into two components, the thermal and the condensed. That's intuitive. And they each have their chemical potential, which in equilibrium, of course, is the same, but out of equilibrium it need not be. Each one has some decay rate, inelastic decay rate due to particle loss and things like that. And also the two components are coupled to each other. Okay, this is the basic scenario. Now, importantly, the two components are coupled to each other in two ways. The one that is more familiar to all of us is simply the flow of particles between the two components due to elastic scattering. Okay? And this flow of particles is what is necessary in order to have true phase equilibrium of the whole system. Okay? So for system to be thermal when it should be thermal, to be partially condensed when it should be partially condensed. Generally, to have the right condensed fraction, particles have to flow between the two components. And this scattering rate, which ensures that, scales with scattering length squared. Now, this is where we are going to break this equilibrium rate by reducing the scattering length. But then, even when you decouple the systems sufficiently, the two subsystems, right, so that they're not in true equilibrium, it would be nice if this condensate still has some equilibrium properties. For example, it has the right shape for a given atom number. Right? And for the condensate, for example, to have the right shape for a given atom number, you actually have to damp the low-lying excitations of the system. Okay, so there has to be still some coupling to the thermal bath. Right? Now, this sort of local kinetic equilibrium is actually provided by Landau damping, which scales as root A rather than A squared. And so this offers an opportunity to study an interesting regime, pretty large regime of experimental parameters, where you can significantly suppress this while you don't really suppress this. Okay? And so the bottom line is that we can think about these guys as two components, right, which are actually at the same temperature, because this will control the thermal distribution of phonons, for example. So they are at the same temperature, but they don't have the same chemical potential. Okay. So this is the basic idea of the experimental sequence. First, we use some respectable scattering length in order to produce a BEC by usual evaporative cooling. So here, blue is the chemical potential of the thermal component, red is the condensate. Initially, we have just thermal component. We cross BEC, now we have both, but the chemical potentials are locked to each other. And then once we have made the BEC, we decouple the two components from each other. Okay? And then they decay in some complicated ways. But one can figure out actually relatively easily that during the subsequent decay of the condensate, the flow of elastic flow of particles is always from the condensate to the thermal component. Okay? So if you shut down that flow, then the chemical potential of the thermal component actually drops faster than that of the condensate, and you get this kind of picture where in total you don't have enough atoms to have a condensate. Mu prime is below mu c, the equilibrium mu is below mu c, but mu naught remains above mu c, and you have a condensate. Okay? How are we going to do calculations in order to know where we are? This is a bit tricky. You have to be pretty conservative in order not to make some circular assumptions. So what we do is the safest possible thing is note that whether the whole system is in true equilibrium or these picture holes and things are in partial equilibrium, or there is no equilibrium whatsoever at all, right? It is always true that there are two extensive variables, extensive thermodynamic variables which are well defined, which is just the total particle number and the total energy. Okay? Whatever the distribution, there's always a concept of total energy and total particle number, right? That's well defined. And these you can get from pictures just by counting stuff, right? The second moment and the total sum of particles and so forth. So this is going to be our presuming nothing input, right? Now, because we have the equation of state, which I have advertised at the beginning of the talk, from N and E, we can calculate all the intensive equilibrium variables. What should be the equilibrium condensed fraction or condensed particle number? What should be the equilibrium mu? What should be the equilibrium temperature, right? Okay? And then additionally, this goes just from N and E. Additionally, you're looking at your picture, you actually know how many atoms you have in condensate, how many you have in thermal cloud. And so you can do sort of partial equilibrium calculations, where from N prime you calculate the equilibrium mu prime, for N naught you calculate the equilibrium mu naught, but without presuming they're the same. Okay? They may or may not turn out to be, right? But you don't have to assume it. And then finally, for comparison, you can also do what we always used to do. I fit the pictures and get what seems to be the effective temperature. The F is for fit from the thermal wings of the distribution. Okay? So we have all this information, and then we can see whether they agree or they don't agree in various regimes. So let's first look at the equilibrium evolution. This is at 83 A naught, so this is a pretty high scattering length. And here we see that we have a complete understanding of, first of all, the measurement precision and also the theoretical understanding of the equilibrium properties of the gas. So what I'm plotting here, say first in the top graph, is the measured N naught versus the red dots versus the green line, which is the equilibrium N naught calculated with no free parameters, just by counting the total particle number and the total energy and using our equation of state. Okay? What we have in the second graph is Tc, which is just calculated from the particle number using the equation of state, and the equilibrium T, which is just a measure of the energy content of the gas, right? And at the bottom, we also have all these three chemical potentials calculated in different ways, right? And here everything just works, right? We see that this agrees perfectly, and the BC vanishes exactly when N naught equilibrium is 0, i.e. when T crosses Tc, and at every point the three chemical potentials are identical, except that mu naught is not defined once you don't have a condensate, but when it's defined, everything agrees. And because here it's trivial, but for the future I introduced two different times. So here Tc is the equilibrium time when the condensate should die based on its cloud's energy content, and the T bar is when it actually dies. And there's no distinction here, but the distinction is soon going to appear. So now we go to some regime where actually equilibrium is not reachable, and we see something quite different. So here we see that this is at 5 A naught. So here the condensate was supposed to die over here after about 15 seconds, but actually lives in the superheated regime for about 40 seconds more. Okay. Here, T and Tc have crossed, right? But the condensate keeps on living, right? And we see what I was saying before, that there's no point in waiting, it's not going to converge. We see that the chemical potential of the condensate and the thermal component actually go away from each other, right? So just this picture tells you this is not a question of transiency, right? It's not a question of waiting and something reaching equilibrium. It's never going to get there. Eventually the BC dies because it has its own problems, right? It has three body and so forth, right? But through equilibration process, it would never reach a true global equilibrium. Now, at this point, I'm going to repeat myself because you could rightly ask, now wait a minute. What do you mean by this temperature when you're out of equilibrium? And at first level, what I mean by temperature is just the energy content, right? Without knowing anything about the distributions of individual states, I can always say this cloud just has too much energy to be condensed. Okay? But actually, it turns out that it does mean more than that. So what we see here is the measured thermal velocity distribution in the thermal component, that's in red. What we see in blue is something which has not been fitted, which is just calculated. From the total energy and assuming equilibrium, we calculate what the thermal distribution should be. That's the green line. Okay? And they're basically indistinguishable. Now you could also say, let's make a thermal fit, but without constraining any parameters, right? And then you get this blue line, which is ever so slightly different. But basically the fitted temperature and the equilibrium temperature for the thermal component are the same. This is not something we understand fully, why the thermal component converges so well to the thermal distribution. And it actually might be related to some other effects people are simultaneously studying at Berkeley and Vienna. There is so-called pre-thermalization effects, where sort of the coarse-grained variables, such as the overall distribution, seem to converge much faster than the actual distribution of occupation numbers for all individual levels. Okay, so we understand this as well, at least that it happens. And it turns out we can also now reproduce it with dynamical calculations that we'll outline on the next slide. So we have checked then how far can we push this superheating effect as a function of a scattering length. And so what I'm plotting here is the highest temperature at which we still observe some, at least an infinitesimally small condensate, and then scale to the equilibrium Tc. Right? And so if you go above 50 or so, then the measured T bar is not distinguishable from the equilibrium Tc. But anyway, this number is pretty low. I mean, like if you asked me 2 years ago, sorry, this number is pretty high. If you asked me, 2 years ago, I would have said that, the 20 or 30 A naught is enough for equilibrium. But of course, this is a moving target. What is enough for equilibrium actually depends on your measurement precision, right? I think the way I would think about it now is that nothing is ever in equilibrium, right? The only question to ask is like, under what conditions does this difference between equilibrium and non-equilibrium become smaller than your measurement precision, right? And so for us, this departure is at somewhere below 40. But if we were measuring TCs to 10% rather than 0.3% that we can do now, then this transition would move around. So somewhere below 50 or so, we start seeing departure, and in the most extreme case, it survives up to about 1.5 Tc, which, if for fun you scale to the water transition temperature, it corresponds to about 280 Celsius. Right? I have no idea what people achieve with superheated water, but this just sounds hot to me. And you see, we can do it even a bit on the negative side for the negative scattering length. Even though only very small condensates are stable for negative scattering lengths, those small guys, still, if absolute A is small, those small guys still live into the superheated regime. And on this graph, I'm already giving it away that we can reproduce these results theoretically. So this red line is our calculation with uncertainty given in pink. And it generally works pretty well, except exactly at A equals 0. Even then it's not a disaster, but it doesn't work so well at A equals 0. But at A equals 0, actually, our model doesn't work. If you remember, I was arguing, this two-component picture, which says we have two components which have same temperature, different chemical potentials, right? Okay. But if it's really A equals 0, then even Landau damping is gone, and BC here just has no equilibrium property. So, we just cannot make claims there. Right? By continuity of physics, right? You don't miss it by much, right? But the calculation is meaningless at A equals 0. So how do we do these calculations? So again, it's very simple. We go back to this picture, and it's the simplest equation ever. N naught dot, the change in the condensate atom number, is the elastic transfer to the thermal component and the decay, right? The inelastic decay. The elastic decay we just calculate from our experimental parameters, like measure the laser power and things like that. There's no free parameters there. And then for the elastic scattering, we use this pretty generic form, which was introduced 15 years ago by some people who were already senior and some people who were not so senior back then, but now they get invited talks at notable conferences. So anyways, this is a pretty generic form, which is it's kind of just usual sort of detailed balance, scattering rate, difference in chemical potential, and so forth. But in order to make this work, again, to advertise our work, right, you have to use the correct equation of state from the very beginning of the talk, right? And so we just look at what is the initial N naught and propagate it in time and reproduce the results as shown on the previous slide. Okay, you can look at this slightly differently also in time. If you we don't have the language yet, I guess, fully developed, and that's why these workshops are good to have for non-equilibrium, the language of non-equilibrium physics. But if I try to construct some kind of phase diagram for this non-equilibrium phenomenon, then I do it in time. So what my axes here are not the usual phase diagram axis. So this is the scattering length, and this is time. And so a horizontal cut through this graph is like that detailed time series I have shown you about 5 or 10 slides ago, right? So what we have at every A, we have a region which is not so interesting. There is a BC here in the gray, but we're not surprised because the temperature is lower than Tc, okay? And then on the far end, there's a region where there's just no BC. There's no surprise there either. But this orange region in between is where the condensate would have died in equilibrium, but doesn't due to superheating, right? So these are the times introduced before. Tc is the equilibrium death time, and T bar is the actual death time. And again, here in the inset, we see our calculation with the data overlaid. Again, it works pretty well, except exactly at A equals 0, where we do miss by 10 or 20 seconds. But you see, it's a minute or so, right, that this state can survive in the superheated regime. Okay, so with that, I'm going to wrap up the non-equilibrium stuff, and I think I'm doing actually surprisingly well for myself with time. And so the last 5 minutes, I want to tell you a little bit about a new experimental system where, in some sense, the biggest news is that we have it. I mean, so far we're focusing on simple stuff, just equilibrium, 3D, Bose-Einstein condensation. In some sense, it's a regression, right? Because you're going back, closer to the textbook, closer to what we have been teaching our undergraduates all along. But I think it's an exciting development that opens many new opportunities. So for a number of reasons, which I don't have fully time to expand on, but I know various members of the audience are familiar with various of these reasons, we decided to try to develop a system for studying Bose-Einstein condensation, but also Fermi gases or anything you want in a uniform potential instead of a harmonic trap. And so this is just a partial list of reasons why you might want to do that. One of our motivations originally was that we want to do many-body physics without relying on the local density approximation. Now, of course, there are many examples. I have to stress this with Martin and Cheng in the audience. There are many examples when harmonic trap doesn't hurt, and there's also some examples where harmonic trap is awesome, right? Because if local density approximation, as Martin would say, if local density approximation works, then actually, it's nice. It gives you the whole phase diagram at once because the density varies across the trap, chemical potential varies across the trap. In a single snapshot, you get everything, right? Unfortunately, there are also important physical examples where LDA fundamentally cannot work. And this is, for example, related to critical behavior close to the phase transitions, and where you have some divergent correlation lengths, right? Where you have no characteristic length scale, and you should not be introducing the length scale yourself with your harmonic trap. This is even more important in 2D that I have been thinking about a lot in the past. But it's also important for the one of the things I actually told you before, this problem of the TC shift in a interacting gas, right? So we have done. Well, I have sort of advertised the success part of the story, which is that we have done by far the best job so far measuring TC shift in a harmonic trap, but actually relating that to the uniform system theory is still not directly possible, right? Because it is the physics of divergent correlations with all length scales playing a role. And actually, the original question asked by Lee and Yang back in 1957 has still not been answered experimentally. For that, you really need a uniform system. In order to measure a TC shift in a uniform system, you need a uniform system. And in 2D, there's many other examples where you want scale-free behavior, and so you want a uniform gas. The other point, which is, I think, quite close to the theme of this workshop, is that if you have a uniform system, then you don't have condensation in real space, as you will see in a couple of slides. And if you don't have condensation in real space, you can have a condensed gas with very low density, right? Because when you reach condensation, the atoms don't clump up in the center of the trap. Okay, it can be about a factor of 100 in density, right? In our work, we have now condensation at about 10 to the 12 per centimeter cubed. Instead of 10 to the 14 or more per centimeter cubed. And so what it means is that other things being equal, the three-body decay is significantly suppressed compared to two-body interactions, right? Which then allows us to crank up both, right? I hope to crank up using Feshbach resonance to crank up the interactions more and go maybe towards a unitary Bose gas, without suffering from three-body as much as we do in a harmonic trap. And then this is really not related to the theme of this workshop, but the way we're doing this in this dark optical trap is also opening some new possibilities for trapped atom interferometry with very long decoherence times. It's very low chemical potentials, very low interaction strength, the level of tens of hertz. There's no AC Stark shifts and so forth. So there's various benefits which might pay off. Anyway, so the way we're doing it is we're putting our gas into this optical box, which is formed by one tube and two sheets. This tube is actually an optical vortex. It's a beam which has about 24 pi winding. So it's like a charge 12 optical vortex. So it has a very flat potential before it hits the walls. And then these two sheets are just produced by cylindrical lenses. Actually, all of this is produced by a phase-dependent spatial light modulator, but these are the optical elements that it mimics. Now, if you have, and then the atoms are sitting here in the center in the dark, and this there the potential is uniform, it's 0. Now, if you had just the optical stuff, then of course the potential in there would not be uniform because you would be living under the influence of gravity, which is a linear potential, so you'd be living in a linear trap. So to get this experiment to work, you also have to cancel gravity to about 10 to the minus 4 level. But that turns out not to be so hard because you have a clear signal. You see whether your gas is balanced or not. It sounded daunting when we started, but it's not actually bad. Okay. So how do we do it? Well, now we're working with a trap which has a fixed volume, unlike the harmonic trap, which has open walls. So of course, if you want to put something into a fixed volume, then you have to pre-cool it so that it's the right size. Okay. So we use one of our experiments. We already have condensation in the harmonic trap. We pre-cooled up to some point. It's not so important exactly to which point, but roughly when the size is right to go into the box, and then transfer over here. This transfer is not necessarily adiabatic. We still don't know exactly where it can be approved, but it's not so important because either way, we want to study equilibrium in a box, so we want to be able to do evaporative cooling in a box anyway. Anyway, so these are some before and after pictures in trap. This is in the harmonic trap. It's actually partially condensed. Here, you can't tell whether it's partially condensed. I can tell you it's not because this was not adiabatic. But even if it were, you could not tell because in a box, there's no real space signatures of condensation. Except, I guess, if you really, really went to zero interactions, because the BEC then would be like sort of the sine function, right, that we learned in second year undergrad, right? But actually, with any interactions, this is sort of in the Thomas Fermi regime, so it's a uniform density. But it would be possible with, say, with potassium or cesium to actually have several thousand atoms and go to the limit where the BEC becomes a sine wave rather than a flat density profile. Okay, so you don't know whether this is condensed or not, and then you have to look in time of flight, and it turns out you have to cool a little bit more. So these are pictures in situ and in time of flight, and we do usual evaporative cooling, just lower the power of the trapping laser, and you see that in trap nothing dramatic happens. It's kind of depressing because you're just losing atoms without anything good occurring. But in time of flight, you actually see that you do get bimodal distribution actually, and also anisotropic expansion because we chose deliberately this elongated box in order to have this signature. This is the detail. Like for experimental experts, I can tell you more later. But we can characterize how flat our box is, and the leading correction we think is something like r to the 13. It's pretty flat. And everything I have said so far applies to other systems like fermions and so forth, broad Feshbach resonance. Maybe not narrow Feshbach resonances because you have to cancel gravity, so you have some magnetic field gradient. But really, even moderately broad Feshbach resonance would be compatible with this. Okay, but for now we've done just, I'll be done this in a minute. For now we have done just relatively simple stuff of 3D Bose-Einstein condensation, and so we can check that this is just condensed atom number, thermal atom number as a function of temperature on one evaporative cooling sequence, and we see where Tc happens, and we can compare that with the uniform system calculation. And it's not great precision for now, but it's within the few percent, or say 10% errors, it agrees. And also, you can. This is sort of a famous thing that we teach students, that the number of thermal atoms below the critical temperature should go as T to the 3/2, but then in a harmonic trap it's T cubed, and now what we measure here is T to the 1.7. Right? So it's clearly much closer to the uniform, and moreover, this distinction between 1.5 and 1.7 is consistent with this r to the 13 that I told you we can independently determine. As the last thing, we have also checked that this condensate is coherent. To do that, we do a slightly more complicated trap with another satellite BEC on the side, whereas this guy is the same as the rest of the talk. And then we just let this go, and you get something which initially looks a bit surprising, but you can figure out that it makes sense. It looks like this with the chirping interference period, because this big guy with low energy just doesn't expand. And so it's always in the near field regime, whereas this reference satellite BEC expands into it. You get a quadratic phase variation along x, and so you get this pairing period. You can reproduce it easily in simulations. And with that, I'm done. This is just a summary of various things I talked about. And just on a personal note, we're also looking for a new postdoc to work on these things. So if you have some good graduating students, let them know. Thank you very much for your attention. Sorry, I always do this. No, you're picking who should ask questions. Yes. I started nodding to various people. Yeah. No. Okay, we did both pick Alan.
try not to compensate gravity. Because if I understand well, if you don't compensate gravity, you are going to have a potential, something like that.
Yeah.
Be amusing. Okay, it's an unusual potential. It's not harmonic.
Yes. It's not harmonic, but it's not a very strong linear either. It's an interesting potential. We have, of course, tried not to compensate. It happens every day before we compensate. but what you see is just no. We didn't do any thermodynamics of it. But what you see here, if you just it all piles up here, it becomes like a red stripe on top.
Yes.
You compensate the other way, it becomes a red stripe on bottom. We haven't studied it much, but it's not going to be linear, right? Because okay, maybe for pure BEC you will get a linear in the Thomas Fermi, but for a thermal gas you get e to the minus linear, if you see what I mean, right? So it's not that different from Gaussian, right?
And I have a technical question about this experiment. What about the residual curvature? Do you have big coils or what?
Yeah, so we have not been as good as you were for the very long expansions in disordered potential, right? We slapped on just something like 50 Gauss. Of course, it's diminishing returns, right? You gain only as root, right? And that's one of the reasons, but turns out not the main reason, which limits the size of our box. So we have something like half a hertz residual curvature, and so if you make bigger and bigger box along this direction,
because you have the choice. It depends on the distance of the.
Yes, in our case, it's attractive. We know that if you go to, we can do easily say 100 milliseconds time of flight, but if you go to several hundreds, we see some deviations and reversal eventually. But I mean, this is just a question of bigger power supply. And for us, the main issue was that because you have this sort of half a hertz and then it's cut off by the walls, you want that. Basically, what our benchmark is that this half a hertz times distance squared, so the variation of energy to be much smaller than our relevant energy scales, right? And it is, right? But one could do even better.
So I apologize if I just wasn't concentrating keeping up on your talk, but I was interested in non-equilibrium.
Yes.
I was just wondering, is this due to residual track heating? What's going on here? How are you controlling?
How are we controlling the?
So your experiment goes for 60 seconds. What are you doing to put it out of equilibrium?
It puts itself out of equilibrium.
So this is due to heating from the track or from free body loss?
Exactly. That's what happens at this time. We use what is already there to drive it into the superheated regime. So you see here the reason that these. Okay, you could say I don't know which one's bigger, right? Okay, there's two effects. Forget even atom loss. Right? Well, okay, I can't forget atom loss, but they're about equal, right? So temperature goes up due to heating, okay, and TC goes down due to decay. Actually, they're about equal contributions, right? But either way, T and TC cross, right? So the ratio of T over TC monotonically grows, right?
So what's your picture? What's happening is the condensate sitting there in this thermal cloud that's getting heated and it's going to react to that, or is something happening to your condensate, or is it a combination of the two?
So it's a combination of the two, but the simplest picture is maybe the first part, right? So I can do one. It's easier to think in terms of heating, okay? So if I make a BEC, right, and then I start heating it, okay? So I make a BEC initially as a cool enough, let's say a fixed particle number, if I knew how to do that. As it become cold enough, atoms start going from the thermal cloud into the BEC, okay? In that picture, it's obvious that if I start heating, the atoms are going back from the BEC to the thermal cloud. That's why I picked that one, okay? And then that's what we stop, right? So we're doing kind of a hysteresis experiment, right? We make sure that the flow is good when it's in the direction we like, and then we suppress when it's in the direction we don't like. Now, you can make the same argument with particle loss. It just involves a little bit more math. Actually, if there was no non-saturation, then it would be easy with particle loss as well. Suppose I have a partially condensed cloud. Thermal atom number has to be equal to NC in a saturated system, which, by the way, our uniform system is, but that will be a later study. So in a saturated system, N prime has to be equal to NC, right? And now suppose you have imperfect vacuum, right? Every time you kill a BEC atom, nobody cares, right? N prime is still equals to NC, and N naught is not constrained by anything, right? Every time you kill a thermal atom, it has to be replenished from the BEC, right? So uniquely, the particle flow is from the BEC to the thermal cloud. Now, when you take into account non-saturation, this is not so simple, but still true, taking into account that equation of state. A very fancy way to say it is that the particle loss is not more prominent from the thermal cloud, but the chemical potential of the thermal cloud is more susceptible to particle loss than the chemical potential of the condensate. And so if you turn off the elastic channel between them, the chemical potential mu prime drops faster than mu naught.
Last question.
I was wondering if this is a wonderful regime to study exactly what you said, like the difference in the phase relaxation and the Landau damping. Could you now maybe, for example, excite phonons and see precisely how Landau damping acts on those?
Yeah.
Could you make vortices and see how they never go away? Something
Yes. That'd be very nice. But I think we will probably not be able to do much more than some sort of collective excitation and see what happens to Landau damping. And the reason is it's trivial in some sense. I mean, this works at low scattering lengths and the thing is small. It's hard to steer it and things like that, right? Okay, we go down to a few microns, right? Right. So something like vortices. I mean, of course, maybe someone's trap or maybe parameters will be found, but. Exactly, that's interesting. Because you could see that it's not only that Landau damping is strong enough, but they say at 40 or so, maybe that's not such a fundamental point, but at 30 or so, you're even in the Thomas Fermi regime, right? You even have sort of the BC should totally have like your superfluid hydrodynamics and everything, right? While just with respect to the particle channel being decoupled to the thermal environment. Yeah. It is a very interesting regime. Yes, it's much more interesting here than just A equals 0. Because if I say A equals 0, you could say like, oh, you have cold water over here and hot steam over here. So what? That doesn't make the water superheated, right? So you want to have some contact.